there's that little lag, so maybe just fill some space to start off with for a minute or two.
Good. Hi, Josh.
Hi, Ben. Should we get started?
Yeah, maybe just wait a couple of minutes, just let people come in through the chat. So keep an eye, make sure we've got a few people here in the attendees list, and then we'll get cracking, yeah?
Great. I think most people are still joining, so let's give 2-3 minutes.
Sure.
Great. Just a couple of minutes. How are you today?
Yeah, I'm good. How are you?
I'm doing wonderful, mate.
Yeah.
Wonderful, yeah.
Did the full team win?
They did.
Yeah.
They won 4-0.
Wow.
Pretty impressive.
Wow.
Harry Kane.
That's only going to happen like once a decade or something.
Oh, even okay. Yeah.
Nice.
Sure. How was your weekend?
Yeah, it was okay. Okay, productive. Things around the house.
Nice.
Yeah.
Looking forward to talking about some metrology.
I think so, yeah. I think we should get into it. Again, ATOS hit live.
A few more. We'll wait for the nod from our director.
Director. Don't even start, boys.
No? Producer? Manager? Agent? What are you?
I'd like to be called agent.
Agent.
Yeah.
Agent.
I like the sound of that.
Yeah. Sure.
Yeah.
Yeah. So another minute or two. Maybe give us a shout in chat if you hear. A little hi, just to make sure we're not talking to each other.
Tell us about the highlight of your day so far.
If you watch the football over the weekend. See if Russ is going to antagonise me about the cricket again. Oh, Elwyn's here. Hello, Elwyn. Good to see you.
Hopefully not flooding up in Queensland.
No,
Hopefully
no.
staying afloat.
You can swim. Hello, Amanda, as well.
I think we can get started.
Yeah,
Okay, great.
sounds great. Let's get cracking. So yeah.
Welcome to the Scan-Xpress Hands On Metrology tour. I'm Josh. I'm an application engineer at Scan-Xpress. I'm joined by
Ben, and I'm a metrologist.
Yeah. So the reason of today's webinar is to showcase some new technology which has been put together by GOM and ZEISS. So GOM have been our traditional technology partner for the last sort of 23, 24 years. They were purchased by ZEISS in 2019. So now we're able to offer the entire suite of GOM and ZEISS metrology equipment. We've got a couple, sorry, before I get into that, the Hands On Metrology is a collaboration between GOM and ZEISS, where they've got some GOM equipment and they've got some ZEISS equipment, and they've put it onto a nice platform, which we'll try and show you at the end of the webinar as well. Two of the Hands On Metrology systems that we'll be showing you today is this one here, which is a ZEISS T-Scan Hawk. It's a handheld laser-based scanning system. And the other one, which is over here, is a GOM ATOS Q, which is a structured light scanning system. We've got some demo projects which we'll jump into, and we'll do some live scanning as well.
Yeah, and talk about some reverse engineering, a bit of inspection, and then some fancy new features which is coming to the software.
Yeah, exactly. So first of all, I'll get started with the T-Scan Hawk. So before I get into a live demonstration of the actual scanning with it, I wanted to show a live project which I did recently. So some of the features between the T-Scan Hawk and the ATOS Q. The ZEISS T-Scan Hawk, I've already mentioned some of the things. It's laser-based, it's portable, it's handheld. Speaking of portability, it all fits into this carry-on case here, so it's very convenient to traveling somewhere and just taking with you, just throwing it in the car or even carrying it onto a plane, whatever works for you. It also comes with a feature or an optional feature called photogrammetry. So photogrammetry is used for predefining our measurement environment for very large measurement volumes.
Yep.
So when we're scanning with the T-Scan Hawk, it starts with about a 500 field of view. And with that 500 field of view, we could quite comfortably scan anything up to about 2 meters in size without needing to do photogrammetry. But for anything from 2 or more meters up to even 4 meters in size, we probably want to use hands-on metrology. We probably want to use photogrammetry.
Yeah.
So photogrammetry, I'll show you in a second, but it's a way to measure the object before actually doing the 3D scanning with it. So I'll jump into a live project that.
Yeah, just while you're getting the live project up, we do have the chat window, so please ask any questions as we go. We might try and answer some as we go, but we might just wait till the end. If there's any easy ones, we'll just answer as we go. We are also using two systems on two different views, so we just need to switch over the cables in between. So just bear with us while we do that. But yeah, this is a great example of this handheld scanning system that scanning a really large object and using photogrammetry.
Yes.
So
Thanks. Ben. So this is a job that we did in Sydney. So I flew up with the carry-on T-Scan Hawk, and we measured this sacrifice sculpture. So this is actually in the Anzac Memorial in Sydney, and it's about 3 meters tall. So if I come here and come to the side view, you can see it's just under 3 meters tall, just about 3 meters tall. So we've got a sculpture here which is meant to be representative of the loss of life during war. Not just the soldier on top, but obviously all the women in his life that supported him and are grieving for his loss as well. So that's what the sculpture is meant to represent. But what we've got is within the GOM suite here, the project that we did all the scanning, and we've got full traceability. So we've got everything in here. If I open up measurements, I've got 2 measurements. I've got photogrammetry and I've got the actual scan data set. Okay, so if I was to come back to my image mapping, what I can see is I can see some of the images which I have captured beforehand using the photogrammetry system. So if I take maybe this photo right here, so what we're seeing here is the image that was captured with the camera beforehand. So what we can see is we can see some of these sort of sparkly because we've been using retroreflective markers, but these are markers which we've applied to the surface beforehand. And we've actually already got them on this part here, so we've already put them on the part that we're going to be measuring today. But we've got them all laid out here, and that's what the scanner uses to identify itself relative to the object. I've also got some coded markers here, and they allow the software to sort of transform all of the photogrammetry images together. So what I do is I put all the reference points over my object, I put all my coded reference points over my object, and then I also keep these scale bars. So these scale bars come with the system, and they allow me to sort of verify how well I performed my volumetric photogrammetric study. So once I've got that, once I've done that, I've got this sea of photogrammetry points basically. So if I get out of that, you can see, turn the scan data up. It's all of these reference points that you can see here. So they're all the way around the objects, and I put them on. The photogrammetry captures all of them, and it gives me feedback as to how well I've done that. So if I come into the photogrammetry module here and turn off image mapping, we can see we've got some deviations here. So it's saying about 0.01 millimeters and 0.015. So we've done a very good job doing this photogrammetry. And then once we've done the photogrammetry, what we're able to do is just do the cloud scanning, which is moving along with the scanner, capturing all the surface data. And you can see that's the end result right there, which is a really high resolution, dense mesh, fully describing the object. What I'll do as well, while I've got your attention here, is just come to our website so you can see some of the photos that we took during the measurement. No, it doesn't want to do that. That's fine. We won't worry about that right now. So that's that little project. So what I'm going to do before, no, what I will do now is I'm going to jump into a live project showing how the 3D scanning works with the T-Scan Hawk.
Sure, but we're not going to do photogrammetry in this one.
No, we're not going to, because as I mentioned at the start, it's got about a 500 field of view, so this object falls completely within the field of view at any one time, so there's no need to worry about any transformation deviations, because it's all going to be captured at the same time.
Yeah, sure.
So I'll open up to another project now. So this is a blank project. So the first thing I want to do before I start scanning this is sort of like the photogrammetry, but not necessarily similar, because I don't have the scale bars in it, but I want to capture all of my reference points relative to it first. So Ben's going to click on the capture reference points for me. I'm going to pick up my scanner, and I'm going to start scanning. And what you're going to see is within the software, you can see sort of a wireframe, and that's sort of the measurement volume that the scanner is looking at any one time, and you can see some measurement dots in there. Those are the reference points that I've already put on there. And as I rotate around, we're going to add new ones in. So it's seeing new reference points and capturing them. And what I want to do is move all the way around until I've captured all of the ones on this side. You'll see some of them turn green, and that's saying that we've captured them at good observation angles. So I'll just go around once more, make sure I've captured all of them on this side. Continue scanning on this side. So one of the other things I wanted to mention is the fact that I'm just using a manual rotation table here, so it helps me to move the part around without actually sort of interacting with it. So when I start scanning here, you should see that they're red, new reference points that I've taken a measurement of, and they're red because it doesn't know where they are relative to the reference points I've already measured. But when I come down to the side and start continuing further around, you can see, there we go, they've transformed together. So I just keep going around. One of the other nice features about the scanner is it tells me when I'm too far away or too close. So at the moment you can see in the scanner I've got these nice green lights. Actually, maybe you can't because it's a little small view. Take my word for it, it's got some green lights there, and if I come too close, it starts beeping at me and the lights are telling me to move away. Similarly, if I'm too far away, the lights are telling me I'm too far away and to come closer. But I've gone all the way around now, I've captured all my reference points and I'm happy. So I'll put this down. Ben's going to click finish scanning for me. So I'm ready to start scanning now, but one thing I do want to do before I actually start scanning is tell the software, tell the system where my rotation table is. Because if I was to start scanning this right now, I'm not going to scan just the part, but I'm also going to scan this table and maybe even the table that the rotation table is sitting on. So that's not something that I want. I only want to capture the data on the part. So what I do is I grab these. These are just a couple of business cards that have some additional reference points on there. So I put them into the field of view. And the software is going to look for some new reference points now. And when it sees these new reference points, it's going to fit a plane through them. And that plane is going to be my sort of background plane. So any data from that plane down is going to be ignored by the scanning system and not brought into the software. But now that I've got that, I've got my background plane defined, I've got all my reference point defined, I can start scanning. Okay, so when I press start now, probably not going to be able to see it in the camera feed, but what you can see on the software is that there's some red laser lines across the part, and they're 14 red laser crosses. And the two cameras look at those laser lines to figure out the 3D geometry. And essentially all I have to do now is just rotate around until I've captured all the surface data. You can see it being built up there. So we're scanning at 0.5 millimeters of resolution at the moment. So what that means is that across the surface, every 0.5 millimeters, we're collecting a data point, which is plenty much for a part like this. And just keep going. You can obviously see in the software where we've missed data, where we need to capture a little bit more data. But we're looking pretty good. So I think we're probably just about ready to say that we're happy with the data we've captured on this side.
Yeah, looks good to me, man.
Yeah, looks great. Okay, so I'm saying that I'm finished on that side, and what I want to do now is flip over and scan the other side. So I'm literally going to flip the part over. Okay. And what we need to do now is we need to redefine where that background plane is, because when I was scanning before, I said the background plane was there and it would be deleting anything that way. So I need to redefine where it is using the same cards. We just need to wait for the software to be ready. Lovely. Thank you, Ben.
All right, all good.
So again, it's going to look for some new reference points. 1, 2. Oh, do that again. Yep. Is it happy?
It's got it.
Yep, it's got it. Great. All right, so I can remove these again from the measurement volume. And now, because I have pre-measured the reference points from both the top side and the bottom side, when I start taking this same data set, it's going to stitch it into the previous data set that I've collected. So you can see here when it starts.
You want me to?
Please click scan.
I'll press the button for you, mate. Don't worry.
Thank you.
We can do it without me.
Yeah, exactly. So there we go. So now we can see the data being collected in that same coordinate system as what we previously collected. And again, same as last time, we're just going to keep going until we've captured all the data.
Pretty easy.
It's pretty easy. Let's go around a little bit more. Okay, do need to go around one more quick time, but I think it's looking pretty good.
Yeah, I think it looks pretty good down there.
Excellent. Okay. So I click the power button in the back. I can put this down. So as we sort of mentioned at the start, the reason we were scanning this is to showcase it as a reverse engineering example. So what we've done is we've collected a dense point cloud, collected thousands and thousands of points over the surface. We've done it from both sides. So we've finished the scanning process, but the next step is to what we call polygonize it, which is tell the software to process the thousands and thousands of points into a single mesh surface file. And then once we've got that, we can do whatever we want with it, whether it's inspection or reverse engineering. In this situation, it is reverse engineering. So let's throw it to Ben now, and he's going to show us some reverse engineering of it.
So what we'll do is we can just switch over this PC. Okay. Yeah.
Link.
So, and then I will share this screen over here, and then we can have a look at that data in the GOM software. So this is a polygonized version of that mesh that Josh just did. So what we've taken is all of those individual scans and stitched them all together to get an STL. And what we can see here is the mesh structure. So what this is the high resolution data of that part. So every intersection of a point is point capture space. We've got lots of data on this part, which is really nice. So what we can do then is as Josh said, we can go ahead and start looking at that reverse engineering process. So we can export the data from the GOM software straight into the ZEISS reverse engineering ZRE package. So all I do is just right click on the mesh there, top option here, export to ZRE. We can also export to DesignX, which is a third-party software, but we're looking at ZRE today, so we can do that. And then that's going to open in here, which is our ZEISS reverse engineering package. So this is where we can start building up our math model around our scan data. Because what we're going to do is, let's say we want to remanufacture this part. We don't want to do that straight from the scan data, because what that's going to do is just carry out any errors from that scan into the actual part. You know, if we look at this plane right at the top here, you can see that it's not plain, really. There's lots of pitting, there's lots of holes in it. It's not that true geometry that we want to then start remanufacture from. So what we can do is actually start creating those math surfaces from this data. So in the ZEISS reverse engineering package, we can best fit these features straight to our scan data. I can do it by dynamic subselection, which can do quite a lot of the hard work for me. All I need to do is just click on the surface I want and select what kind of features. So in this case, it's a plane here. What I can do is just increase and decrease the selection. So I'm looking at is that orange number of that orange selection. Make sure it's a nice even coverage across that whole feature that I want. Now what we can do is actually calculate those current parameters. So what it's doing is it's fitting that geometry to that selected points and telling me kind of what this reference axis is. Now I can accept that, but let's say we want to reverse engineer to design intent, as in how this part was supposed to be manufactured. What we can do is come in here and actually edit these features. So what this is meant to be is maybe let's take 0.2, the Y is probably 0, and the Z is probably a 1. And what we can do is then best fit our geometry, and that's going to best fit. It's going to calculate that plane to those reference geometry. So you can see a nice plane there. That's exactly where we want it to be. So we can create that one, which is done. And now what we want to do is maybe select, I don't know, maybe like this in a ball right here. So this is a cylinder, so let me select the cylinder. I'm going to again select that surface. We can see that orange sub-selection right there. We can adjust that by increasing that. So what I want is a nice even selection all around that cylinder and using as much of this good quality data as possible. Again, we can calculate its current values and have a look down here. You know, that radius, 28.6 maybe, 28.6, and then we can calculate that best fit geometry. And that's going to fit that cylinder exactly where we want it to be, right in that feature right there. Now, all this is going to be now is just fitting all of my surface features to this geometry, building up the model, and then eventually combining them all together to create our solid, so cutting them all through. It takes a bit of time, but that's kind of the general process, selecting them and then editing these features. But ZRE is a pretty fantastic project. This is only showing a tiny amount of what's really possible with this and within this. One of these great features is called Tool Correct. Talk to me about Tool Correct, Josh.
Tool Correct is a cool feature within ZEISS reverse engineering. It does literally what its name is, which is Tool Correct. It corrects tools. So we've got a nice video which we can play here. But what it is a way for us to measure a component that comes out of a tool, whether it's a casting tool or a plastic injection molding tool, and then get information about how that part that we've measured deviates from the ideal part. But then rather than telling somebody else what the problem is, what it's actually going to do for us is correct our tool. So it's going to modify the CAD model of the tool, whether it's a casting or a plastic injection molding tool, so that the part that actually comes out of that tool is closer to the design intent.
Yeah, exactly. So it's just reducing those design iterations that you might go through, where you change it, test it, measure it, change it again, test it.
Yeah.
What we can do is reduce those steps down. So we just take the part, and it's going to actually adapt the CAD model to the captured scan data of that part. Let's show you this video. It's a really cool feature. So we'll play this right now. Yeah, excellent. Really nice video showing that feature. So yeah, we just had a couple of questions while that video was playing. Maybe we'll answer these straight away. So
Yep.
Josh, the software that we're using.
Sure. So Frank's asked what software we're using. So the two software that we have shown the scanning in is called GOM Suite, GOM Inspect specifically, and then ZEISS Reverse Engineering. We've done the reverse engineering. But maybe one thing that I can just show really quickly before we proceed, just to make it crystal clear, if I turn screen share on here, what we can see here is this is the GOM Suite. So whenever you want to access any of the GOM softwares, you open up this GOM Suite, which is this sort of black and blue icon here, and this gives us access to all of the GOM softwares. So we've got GOM Inspect, and that's where we've done the scanning so far today. It's also where we're going to continue doing some scanning and some inspection. And then all the way down the bottom is the new ZEISS Reverse Engineering software. So that's where Ben showed the reverse engineering of the casted part and that scan data that we had. Okay,
Yeah,
another question?
Yes, another question from Amanda then. So would this work on a small injection molded part, so it's the size of a pen lid? So absolutely, would those features within the ZEISS Reverse Engineering software would work on parts of relevant size. What you might want to consider though is the scanning system that you use. You know, this laser scanning system that we've just shown is great for medium to large components, but it probably won't get quite the resolution of a part, the size of a pen lid. So that is where we might want to use something like the ATOS Q, which leads us quite nicely into this, because what we'll do is show you high resolution scanning that works on small components like that.
Yeah, great.
So let's get started. What we're going to do is dive back into that GOM Inspect software, and now this time it's going to be configured to start scanning with our ATOS Q right here. Start sharing that, and then Joshy can carry on.
Great. So same as we did with the scanning and the ZEISS T-Scan Hawk, with the ATOS Q we still scan into the same software, the GOM Inspect suite. And what we can see here in this top left corner is a camera feed, so I can switch this from just the left camera to both the live views, so you can see what the left camera of the system is seeing, what the right camera of the system is seeing, and we can see we've got our part in the middle of the software there. So one of the really nice things that they've introduced in the 2021 version of the software is this workflow assistant. And the workflow assistant is really great for somebody that may not be too experienced with the software, someone that may not have been formally trained with it. But with the workflow assistant, they can come along and follow these prompts and get some really good scan data without too much effort. So the first option within the workflow assistant is asking us whether we want to scan a single part or we want to scan multiple parts simultaneously. So there is an option for us to do multi-part scanning where we can divide the measurement volume of the whatever measuring system we're dealing with into pieces of a pie, into segments. But today we're just dealing with one part, so I'm just going to say scan a single part. So then the software asked me for some questions about the reference points. Are we using photogrammetry? If I might have done a photogrammetric study, if it's a particularly large part, for example, or if we're using a reference point frame, or if we want to import some pre-measured reference points, or if we want to scan with the rotation table. And we want to scan with the rotation table today. So what we've got here is a GOM ROC 350, which is an automatic rotation table, and is recommended to come with the system because it saves a lot of time. So I'm going to be doing that. I'm going to scan with the rotation table. So I'm going to bring up my camera again, switch back to just the left camera, and say start scanning with the rotation table. It's going to ask me for the temperature. And what you'll see in a moment is the left and the right camera project a series of lines horizontally and vertically across the part. We've taken that first measurement there now, and what it's asking for me is to define our cutout plane. So similar to how we did it with the T-Scan Hawk, where we manually defined it, this time it's automatically defined it for us. So it's just scanned the bottom of the table there and figured out where the background plane is, and it's asking us if we want to cut that out, and we say, yes, please, we want to cut that out. So now we continue, the rotation table rotates. Again, the projector projects its lines across the part. The two cameras look at those lines to build up very high resolution detail mesh, and you can see the speed at which it's doing.
What kind of resolution are we working to with this system, Josh?
At the moment, with the ATOS Q 12 megapixel system over a 270 volume, it's 44 microns.
44 microns, that's about 10 times the resolution to the laser system.
That's right, yeah. So it's very, very high resolution, very, very accurate data. So we can see, if we come across here, we can have a look at some of that very high resolution data. Now, actually, what we're looking at here is just a preliminary version, just sort of a way we can get an idea of if we've captured all of our data or not, and we're happy with this. So what we need to do now is flip the part over and continue scanning on the other side. So I'm going to say prepare scanning second side here in the workflow assistant. It's ready for me. Now I flip the part over on the rotation table. And again, I can say scan with the rotation table. Okay, so similar to last time, the system projects the pattern across the part. It's going to automatically detect as I cut out the plane for me, which is right there, and I say, yes, please, get rid of that. And again, we continue rotating and scanning and rotating and scanning. So yeah, this is a complex plastic injection molded part. So because of features, it's a bit more well suited to a higher resolution, more accurate system like the ATOS Q rather than the T-Scan Hawk. The other benefit of having a more accurate, more repeatable measuring system is the fact that we've got greater confidence in the measurement data, and that means we're able to make good decisions when we're doing our inspection.
Yeah, exactly. That's why this might be used for, an inspection type project, whereas this system right here might be used for a reverse engineering.
Yeah, great.
Yeah.
So what we've done so far with the ATOS Q is we've scanned one side, the rotation table went around, we captured that data, we flipped it over and measured all the way around again. What we've got to do now is we've got to put those two halves together. So we can say, again, within the workflow assistant, we can say transform second side into first side, and the software is actually going to do this for me automatically. So we can see here we've got one side over there in burgundy and the other side over here in grey. And we've got some quality feedback as to how well we've actually done that transformation between the two halves. And the software is telling me it's a high quality transformation. So we're happy with that.
Congratulations.
Thank you very much. So once we've got this data, similar to how we did it with the Hawk, we've collected our dense point cloud. We want to now polygonize it into a single mesh file, and then we can start doing our inspection workflow with it. So Ben, you're going to jump in to another project where we've already completed the scanning.
Yeah, exactly. So all of that's going to be doing is just taking over from exactly that step where we've just polygonized all of this data. So what you can see here is this is kind of the output from this GOM file, which is this high resolution point cloud of data. Now you can see here up in the information, we've got just under 3 million data points captured on this injection molded part. So it's very high resolution, really good quality data. This is kind of the standard output of data from this ATOS Q, and it's really it's a fantastic measuring tool for getting this really good quality, high resolution scan data. But now what we want to do is actually inspect it. Yeah, we've got our part, we've scanned it, we've got our manufacturer drawing, we want to see what kind of results we get. So I've got the CAD model for this part, which is right here, but something's wrong, Josh.
Looks wrong, doesn't it?
Fantastic. So what we need to do is start doing some alignments. So what we can do is do a pre-alignment to start with. Now what this is going to do is just a global best fit, just slam these two parts together so we can start our inspection process. It is just a best fit, but we can use this to actually start doing some of our inspection. So what we've got along the top bar now is some of our quick access shortcuts, so I can do my surface comparison. It's usually a good way to start the inspection, and what it's going to show is the closest point on the scan data to the closest point on the CAD model, and show that up as a color map, so we can get some initial inspection on how good our part is. There's input tolerance, maybe 0.2 mil, and then maybe just change our color map right here to, let's say, 0.5 mil. And then we can start having a look and seeing where our part sits. So any data that's blue means that scan data is below the CAD model, and anything that's yellow or red means the scan data is above the CAD model. We can see that overlay here if I just bring up the CAD model and how that relates to our scan data, which is that color map. Now what we can do is apply some deviation labels to right here, and by just holding down my control key, I can create some of these features, some of these deviation points straight on that color map to know exactly what the deviation is in any of those localized areas. Now, what we can then do is, we want to inspect back to a manufacturer drawing, right? So we can't just rely on a best fit. We need to rely on an actual solid alignment. So I've already created a few features right here on my CAD model, which is some planes and some cylinders, which relate to these dating points. So let me just apply my fitting element. Essentially what I'm doing is saying fit all of these elements to the scan data in the best way you possibly can, which is done. And then I've got my reference point right here, which is my reference construction. And then what we end up with is these 6 points, which are my dating points defined by my drawing. So what I can do is do an RPS alignment, select those 6 data points, and that's going to align to those points. Now that's a fixed alignment rather than that best fit. Now what that does is it's going to add in a new alignment to my tree, which is just on the left-hand side. So you can see here, I've got my initial alignment, which is that best fit, and underneath that, I've now got my RPS alignment. We can have as many of these alignments as we like, so we can do multiple alignments to every part. So what that means is maybe on a casted part, we can inspect our casted datums, as well as doing a best fit or a localized best fit on the surface, and really get a good understanding of what's happening with our part. Now this is going to update all of my inspection live. So if I just bring up my surface comparison, it's just going to update that new alignment. And what we'll be able to do is switch between these alignments and see how that alignment is going to adapt to, is going to change that color map. So see what's happening there. That's how we can get a really good understanding of exactly what's going on with our part. So once we've done this and we've got our color maps and we've kind of got a good understanding of what's going on, then we can start doing some actual feature-based inspection. So this is where we can create some features and do some inspection as you might see on a drawing. So let's just take some features here. So we've got this conical shape right here. I'm just going to create a fitting cone to that by just, again, control clicking on the surface. Fitting element to snap that to my actual scan data, and then we can do our inspection. So we've got this little circular widget right here. This is called the iInspect, and it controls all of my dimensional checks and all of my GD&T. Everything's controlled here, and it actually updates depending on what got selected. So I've got a cone selected here. It's going to give me everything that's relevant for a cone. So in the checks, it's just an angle because I can't do any diameters or radius inspection on the cone. What we can do is apply a tolerance, and that's going to give me my pass-fail check, and I can go into my tabulated report and create all of my intuitive go, no-go reports from there. We can also do all of our GD&T. So let's just say we want to do a flatness check. What we can do is come over to our CAD model right here, select the flatness check, and then click on the surface. And that's going to do everything for me. It's going to create on the nominal, create on the actual. All I need to do is input a tolerance. So that's all done, and we've got our GD&T flatness check. But the great thing about GovInspect is you don't have to stop the inspection here. Just because we've got a green tick, we've got a pass, doesn't mean that the inspection needs to stop. We can go into much more detail. On this plane, we've got probably 10,000 individual points, and we can inspect every single one of them. So what we can do is show the color deviation representation, bring back up our scan data, and then maybe reduce our tolerance legend down just slightly. So let's go for 0.1 of a mil. And then what we can see here is actually that surface comparison again, but this time it's just related to this flatness check. So what we can see here is, it's a plastic injection molded part. These are the injector pins, and we can see the 3 injector pins right there and how they've impacted that surface. Now, just because it's passed our flatness check doesn't mean that it's not still having an effect on that surface. Now, by using these tools and maybe going into some more detailed analysis using some SPC or tracking some data over time, we can see if this tool is wearing and if it's going to fail at some point, and have that predicted failure built into the software, so we can do this ongoing analysis of our parts. So the level of detail that we can go to with the inspection reports is huge. So we can have these go, no go, pass, the parts passed, it's fine, it goes on down the line, but then we can have these additional reports going on in the background where we get all this extra additional information. Pretty good, right?
It's amazing.
I'm so good. I'm so good. So another feature that I want to talk about, and this is where I get probably excited about. I've been excited before. So this is a new feature that's coming out to GOM specifically for plastic injection molded parts. And this is called dewarp. So what this is, when you get plastic injection molded parts, as they come out of the tool, there's going to be inherently some warp, some twisting, and that might be related to the cooling, it might be related to how the material has been injected into the tool, and that's going to have an effect. Now, what we usually do to inspect those is we physically clamp them. So we'll have a fixture that physically clamps them into their assembled position, and then we can inspect them in their assembled position. The problem with that is that they are expensive to manufacture, they take time to manufacture, and if we're working on a development part, maybe we don't want to invest in having those fixtures just for inspection. What we can do within the software is this thing called dewarp. And what that's going to do is adjust our scan data to allow for that warpage. So we can actually constrain it and constrain the live scan data within the software. I've got a short video. I'll show you how it works, and we can talk about a bit more about those features, and I can get even more excited. So let me show you this video. I'll dive back into right here, video right here, and dewarp. Yeah, wonderful. So that's dewarp, showing dewarp in action. Brand new feature coming this year to GOM Inspect. So GOM actually developed these kind of tools and this kind of feature for sheet metal parts, and actually doing this. It's called adaptive fixturing. It's called not adaptive fixturing. It's called virtual clamping. Yeah, to automatically clamp those sheet metal parts back to this kind of virtual fixturing to simulate that effect. That was quite an in-depth process. It involved getting a different package and a different license involved in the software. The plastic injection molding part is actually available within GOM Inspect. So it's a much simpler process, and we can do it on pretty much every injection molded part. And what we do is we input some critical dimensions, such as the material properties, the CT, and things like that. And then it's going to do this calculation of adjusting that and actually, applying those over-constrained forces to our captured scan data. Really exciting feature, and I'm really excited to give it a go, and then have a chat with some of our customers who are already using these systems, and how these features can just be bolted on and really improve their manufacturing process and save time and eliminating the need for creating those really complex and inexpensive fixturing.
Yeah.
But yeah, great. I've got a couple of questions which we'll answer, and then just please ask any more as we go, and we can just dive in. But yeah, I think Bruno's got a great question. Jose got a great question about the surface texture. Now, surface textures are a tough one. There's these scanners are very high resolution. We can capture a lot of information. And if I just show you back in here, if we just turn the screen sharing on, I'll dive back into that casted part. You can actually see a lot of those surface nuances on that casted part, and a lot of it's going to depend on the system that we use and the resolution of that system. When it comes to kind of the surface finish, maybe an RA or an RZ value defined on a drawing, these systems really aren't designed for doing that level of inspection. We've got other tools that we use for capturing those kind of surface finishes. But what we can do with these systems is we can actually detect surface defects. So that might be a scratch in the surface, it might be some damage caused by it, a dink or a nick, or yes, some small scratches. And we've got features within the software which will actually analyze those surfaces automatically. And we can apply different parameters to detect those defects automatically. hopefully that answers that question. If it didn't, just please ask again in the chat. Josh, we've got another question right there.
Davis has asked, can you set up the software to do those GD&T checks on multiple sample parts without resetting everything up?
Yeah,
yes, you can. The software is really well suited to that. What we do is, once we've measured a part for the first time and we load it into the scan data, load it into our software with the CAD model, we can set up all our inspection tasks, our diameter checks, our position checks, GD&T checks, everything that we want to measure. And then what we can do is we can save the project as a template. And what that means is that next time the part comes off the assembly line, or we've got another part as inbound goods and we want to measure that, all we do is we measure it, drop it into our template, and then the project will automatically update. So all of our checks will be automatically updated, and we've got that result and that feedback straight away without having to recreate all the elements.
Yeah, exactly. Yeah, and within the GOM software, it's called Teaching by Doing. Essentially, every project that you do in GOM is a template.
Yeah.
And all it is just just scanning in the next part if you want, and it's going to update all of those inspections, all of the report pages, really nice and easy.
Yeah. So we have run to the end of what we wanted to show you, so we will stay on the line for a little bit and just let a few more questions come in, or if anybody here in person has any questions as well. One other thing that I would have liked to have mentioned earlier is that this technology that we've showcased here today is available as a sale, so you can purchase it from us with the distributors, but we also offer it on a service basis. So if you've only got a couple of parts that you'd like to measure and you may not have the need to invest in a full system, then we're available to offer that as a service basis as well. And we can also offer the add-on of reverse engineering it and constructing a CAD model for you, or performing quality inspection as well. Is there another question?
There's not. There's just a great thanks, which is wonderful. Thank you very much. I tell you, let me just show you a quick website, which is a really nice resource. So I'll just make sure it actually brings up. We haven't had much luck in showing websites today, so maybe that was a bit ambitious. Yeah, here we go.
Show the screen.
So let me just share my screen. So this is a website that's developed by GOM and ZEISS. And it's called Hands On Metrology, and it's effectively about what we're talking about today. So we've got a number of different scanning systems, which you can see right here. So we can go down to sessions, and we see the different scanning systems which are kind of involved in this family. So we've got the T-Scan Hawk, which is this laser-based system, the Q, which is this system right here. And these are going to be like video tutorials on how these systems work, how to set up the system, unboxing, calibrating the sensors, and some of the different features that we've talked about. There's also the software functions. So I've already shown you some of those inspection softwares. This is just, again, just video tutorials talking through some of those features. One of the things that we didn't mention, and we probably should have mentioned, is the software is free. Yeah. It's a free download, the GOM Inspect software. And it's a fantastic software. What you can do within that freeware is pretty much all of the inspecting and reporting that we just showed you, all of those dimensional checks, all of those inspection, GD&T, and all of those color maps. So what that means is you can do offline reporting. So, let's say you've got one of these scanners that's working 24 hours a day and you want to do some offline and reporting. You can just take those projects and do that yourself on a separate system without needing the dongle. The other thing is, if you send us a part that we scan for you, then you don't need to rely on us to do all of the reporting. We can give you back the actual full project, and you can do some of that reporting offline within that free software. It's a great resource. And using that Hands On Metrology website to learn how to do some of those simple steps.
Yeah. No, it's a really good resource.
It is, isn't it?
Heaps of information on there.
Yeah.
Great. There's no other questions. Any questions in-house? You're wet.
Yeah. Any questions from our agent? No, gives us a thumbs up. Agent's fine.
Well done. I think we have one more question that just came in.
Yeah, so that's a great question. There are lots of training programs. So GOM have got a couple of different ways of trying to teach people the system, because what we've shown you today is like the simple workflows, but these are really in-depth inspection tools. You can take as much out of them as you need. So the simple processes are quite easy to learn, but some of those advanced features do require training. That Hands On Metrology is a great resource. There's also inbuilt training within the GOM software. So again, let me just share my screen, and I'll show you within that GOM software. Let me just open up this project right here. Now, what GOM have got is within all of their tools, they've got the inbuilt direct help. So let's just say this cone here. What I can do is hit this little question mark. That's going to take me to the direct help built within the software. It's going to talk me through exactly what is involved in constructing this fitting cone, talk me through all of the menu elements, anything that might affect that tool. It goes into a huge amount of detail in exactly what's going on in creating that feature. And that goes for any feature within the software. It's going to go into this much detail on how to create it. So this will answer a lot of the questions. But the other thing is that the GOM have got their own online training portal. So, GOM training, and what you can do from there is full-on training courses. So these are, a couple of hour courses or maybe even 2 or 3 day courses. You can sign up to them online, follow the video tutorials online. There's interactive workflows, and you can actually do it alongside the instructor, as well as quiz at the end to pass your training process. And that goes for loads of different features. Simple operation of the scanner to full-on GD&T training, scripting training to learn Python, all sorts of things, all available through that GOM website.
Yep. Some of them are paid for, but there's a lot of free ones on there as well that you can access.
I'd love to show you it, but it would just show you all of the courses that I've currently started and haven't completed. So it would just embarrass me, so I'm not going to do that. It's brilliant, yeah. But if you need more information about those training that's available through GOM, just talk to us directly. We can talk you through that. The other option is, of course, we offer on-site, in-person training along with these systems, and more than happy to do that as well.
Yeah. And international too. We can go to New Zealand if they're letting us in at the moment.
Yeah.
Not sure about that.
Absolutely.
Or international to WA.
To WA, yeah. So it would be great, wouldn't it?
It would be great to get over there.
Yeah. We go to Queensland, but we need to wear swim trunks.
Yeah.
So,
yeah.
Yeah, these scanners do not work underwater, so sorry, Queensland, you're fresh out of luck.
Yeah. Another question just came in.
Maximum object dimension T-scan able to capture is a great question. Where you go, Josh?
Yeah, so I sort of briefly touched on this at the start. As we mentioned, the field of view of it is about 500 mil, so at any one time it's sort of looking at about a 500 millimeter area. And without taking the process of photogrammetry, that means we could measure up to about 2 meters quite comfortably without worrying about any tiling errors or volumetric errors. If we wanted to measure an object larger than 2 meters, sort of 2 meters to 4 meters, or you push it for a little bit bigger than that as well if you wanted to, you need to incorporate, or it's recommended to incorporate photogrammetry so you don't have any loss of volumetric accuracy as you start scanning from one position and continue moving to the other end. So about 4 meters is what we'd probably say.
Yeah, 4 meters you can extend it a bit further. I recently did a couple of interiors of aircraft using this T-scan, and they were a good, maybe 10 meter long sections. So you can extend it. But what we can also do is incorporate the photogrammetry system from GOM if you really did want to scan a much larger object. The great thing about that is you'd be able to capture a really large object, but only scan the areas that you need. So rather than having to scan everything, and it will all be in that constraint, that same alignment system. But yeah, if there's anything that you're particularly interested in, just let us know and we can talk about it in a bit more detail.
Yeah. We do have other systems as well. So both of the systems that we showed you today are sort of geared towards small to medium sized objects. We do have other scanners which have a much larger measurement volume. One of the other GOM systems, the compact scan, thank you, has a 1.2 meter field of view, so you can quite comfortably scan objects up to 4 meters in size without worrying about photogrammetry, something like that. So if you've got a particular application, please get in touch with us and we can match the best system to your application. It may not be what you've seen today, but we just wanted to show you some of the hands-on metrology products. Wait a couple more minutes for any questions, but we're just about there.
Yeah.
A little bit more about Scan-Xpress, us. So we're here in our head office in Melbourne today. We've also got an office in Sydney, and we've got a couple of operators up in Queensland to help you with on-site measurement tasks, and we've got somebody in WA that helped us out as well. So we've got quite broad coverage across Australia. Not just 3D scanning systems, we also offer the full ZEISS metrology range of measuring systems. So we can also offer CMMs, CT scanners, vision measurement machines. Sorry?
Well,
minutes?
I ran out. 50 minutes, mate.
50 minutes.
Good solid, good solid time. Yeah, we'll stay here for another minute or two if there's any other questions that come in. But yeah, just fire us over an email if you got anything specific.
Yep.
And the recording of this webinar will be available. So
Yes.
you can see our lovely faces again for that.
Exactly.
Thank you very much, guys.
Thank you, everybody. Bye-bye. Happy days.
Thank you, Agent.
Agent Angel.
We'll take it off.
Signing up.
Wave bye, wave bye.
Bye-bye.
Camera.
Bye, camera.